Okay, welcome to the second part today. Welcome to the second part today. Yeah. As I said, this algorithm is not necessarily already a good algorithm because maybe n can become arbitrarily large, but a nice theorem tells us that it can't. Ooh. So remember, this E tor Q is all the torsion points with rational coefficients together with the point at infinity. So in this group, all torsion points which can have order, I don't know, is either z modulo nz with n between 1 and 10 or 12, or z mod 2z cross z mod 2nz with n between 1 and 4. And this is really crazy because those are only a handful of groups and they're all very small. So this checking n, we only have to check for some numbers because it can have order 12, I think, is the largest that can happen, or 16. So the groups are extremely small. So we can write an algorithm, we can write a program for a computer that will be very fast, because computing the discriminant is just computing something from given coefficients that we have. Find all divisors of the discriminant. Okay, if the discriminant is a product of many primes, then this can take a few seconds maybe, but usually it's just a product of a few primes. Then find all x such that y squared is equal to x cubed plus ax plus b. This is also just some arithmetic because we have formulas for solving a cubic polynomial. And then for all those pairs xy, compute n times xy until either the coordinates are not integral anymore or we get the point at infinity. And this is also pretty fast because adding points is also just computing some polynomials, adding, multiplying, and we have to only do that a few times. So what we will now do in the second part of the lecture is with some black box that we assume, we will prove the Nagel-Lutz or Lutz-Nagel theorem, and then we will compute at least one example probably of an elliptic curve where we use this algorithm to find all the torsion points. Okay. So the one black box that we use which is in Silverman-Tate chapter 2, section 4. And I think it also basically uses a bit of p-adic numbers maybe, or valuations at least, but also not things that are too complicated or where you need too much knowledge before you can understand it. But it's more like technical and some computations, but what they prove there is torsion points have integer coefficients. So this is what we want to assume. So what is left to prove is that if we have a torsion point, then either y is 0 or y divides the discriminant. And this is pretty fast to prove, but it's also very nice to prove, because that's exactly what I want to do here, hands-on and computing some easy calculations that will enlighten you and see why everything belongs together. So the lemma that we want to use and want to prove, and this is Silverman-Tate chapter 2 section 3. I call it x1, y1. Be a point on an elliptic curve. I will try to put this in 3 parts. So what we want to prove is that if we have a point on an elliptic curve, so here everything is rational. The elliptic curve is rational. Let me write this here, so over Q, and the point is also rational. And, well, it even has integer coefficients. Then it's either a 2 torsion point, where because the y coordinate is 0, or the y coordinate divides the discriminant. Okay, so how do we prove it? We take those assumptions and say if y is not 0, then we want to find out that y divides the discriminant. So assume y is not 0. If y is not 0, then also 2 times p is not the point at infinity, because those are exactly the points with order 2, or the points of order dividing 2. So we can write those coordinates, let's call them x2, y2, and by assumption they're all integers. Okay, so we use the duplication formula from here, but we use another way of writing it. Or is it the same? Okay, let me see if that is what we have here. I think it is, because So f prime of x1 is 3x1 squared minus a. And it could be that I missed something there, that I have a typo there. Let's just assume that everything is correct here, or that we have a typo up there. But this, let's assume this is correct. So since x1 and x2 are integers, this is of course also an integer. So this is an integer. So 2y1 divides this. So since 2y1 divides this, also y1 divides this. And we also have, because y1 is just the y-coordinate of this point, which is a point on the curve. So y1 squared is f of x1. The y1 is the y-coordinate of this point, which is on the curve. So y1 y1 squared is f of x1. And now we will use at least a black box, or maybe I will put it on the exercise. The discriminant of the elliptic curve is also the discriminant of this polynomial. And in probably like algebra 1, you may have learned that we can find polynomials such that r of x times f of x plus s of x times f prime of x is the discriminant. And since from here we can see that that y1 divides f of x1, and here we have that y1 divides f prime of x1, then we also have that y1 divides the discriminant. And it's actually also possible to change the proof a bit, or a bit more, and prove in the end that actually y1 squared divides the discriminant, which makes the algorithm a bit more faster, because we also only have to look at the primes, look at the numbers that divide the discriminant in the square. But here, for our purposes, it's enough to have this. So this is what we wanted to prove. Okay. How can we prove now the Lutz-Nagel theorem with this lemma? I think in the book they call it Nagel-Lutz, but as I learned it, it was Lutz-Nagel. I think one of them is a woman, but I don't remember which one. So, yeah, then it's good that we write Lutz-Nagel. There's so few women in maths, and we have to always put the women in front. I think there was once a petition to rename this university to Eminöter University. That would have been so amazing. So amazing. I love her. I had a cat named after her. Okay, so let's prove this theorem. So let P be a finite order. So we have two cases. If P is of order 2, I can say order 2 and not order dividing 2 because we excluded the point at infinity anyway. So if P is of order 2, then by our black box lemma, it has integer coefficients. And by some proposition from the beginning, we also know that the y-coordinate is 0. Everything is fine. If P is not of order 2, then we also have our black box that says torsion points have integer coefficients. And of course, 2p is also a torsion point with order 1/2, or with also finite order. So we can use this lemma. And we can use this lemma because P and 2p have integer coefficients. And it says then either y is 0, but this is, we excluded this because this was the other case, but then we have y divides the discriminant. And this is the proof. But it's very important to keep in mind that this is only true in the one direction, not the other way around. Not all points that have integer coefficients are torsion points. There are torsion points, there are points of infinite order with integer coefficients. So there are infinite order points with integer coefficients, but there aren't points of finite order with rational coefficients. The points of finite order all have integral coefficients. Okay, then let's calculate some example. I'll erase this. I'm writing down the page number, but since you probably or may have another edition, you should probably concentrate more on the chapter and section. So we want to consider the following curve. It's not given in short Weierstrass form. So we either look at the formulas in front to compute the discriminant in the long form, or we just read off the discriminant from the book, but I want to compute it explicitly from here. So we do this algorithm here, compute discriminant. So Silverman, chapter 3, section 1, tells us that if the curve is in the form then the discriminant maybe I should have chosen an easier example, but now it's too late. Minus let's just leave out the calculation of the discriminant and read it from the book. It's 3. Yeah, on the exercise sheet I will put examples in short Weierstrass form. That makes everything easier. So, it's 3! Which is very nice because 3 doesn't have too many divisors. So, the step 2, find all y in Z such that y is 0 or y divides the discriminant. So the possibilities are 0, 1, minus 3, and 3. So now we have to find out for which x we can find, for which y we can find an x. So start with y equal to 0. Let's call it y. Yeah, y equal to 0 means that x cubed minus x squared plus x is 0. So we can factor out an x. And this is a third root of unity or something like that. One moment. Let me see. Well, let's just put the book away. Okay, so x equal to 0 is one possibility for the solution here. And what other integral solutions can we have here? If we have a polynomial and we want to have integer zeros, then it always has to be a divisor of the last term. So it has to be either 1 or minus 1. But if we put in 1 or minus 1, it's not 0. So then this is the only point with y equal to 0. Let's continue with y equal to 1. Then we have x cubed minus, x squared plus x is equal to 1 squared, which is 1. So we put this on the other side because it's easier. Okay, here we have at least 1 as a solution, because 1 minus 1 plus 1 minus 1 is 0. Maybe we start a list here. So point at infinity, 0, 0. We have 1, 1. Minus 1 is not a 0 here because it's minus 4. Yeah, so this is all zeros here is only this 1. The same, of course, for minus 1, because nothing changes if we put a minus here, because we have y squared. So this is also a point. You can stop me if I make a mistake here, because this is not in the book. I thought it was in the book, but... Okay, next thing is y equal to 3. So we have x cubed minus x squared plus x minus 9. We can do both at the same time. Is 0, so we have to check if either 1, minus 1, 3, or minus 3 is a 0 here. So 1 and minus 1 are not. 3... also not. Minus 3. Also not. Correct? I think so. Huh? What? Oh yeah, yeah. Right. Oh God, now we have to... Okay, but this is definitely not 0. Both not 0. So let's see if they have the same result. Yeah, nice. They have the same result. So we found all torsion points, and now we can also think about which group is this. So this is a group of order 4. Remember that in the first part of the lecture, I gave you the exercise for the exercise sheet to find out what those groups look like. And now we want to find out how this group looks like. Let's call it G. And yeah, let's think about it. So it has 4 elements. So it's either z mod 2z squared or z mod 4z. Yeah. Oh yes, sure. Sure, right. We are not finished with the algorithm yet. So let's do this afterwards. Okay, so here it's easy to check it. It's the point at infinity. Here this is also clear because it has y coordinate 0. So we also only have to at those 2 points. And wait, what did I want to say? Okay. So we could now either just calculate twice this point, 3 times this point, and 4 times this point, or we could also just compute twice the point and 4 times the point, because 3 times the point will not be 0, because those 2 points, let's try to solve this with a bit of group theory. So Q and R, they have the same x coordinate and just the minus in front of the y coordinate. So Q is minus R, and minus Q is R. This doesn't tell us a priori that there are torsion points, but it tells us that if one of them is a torsion point, the other one is also a torsion point. Which means that this group either is of size 2 or of size 4. Which also means that either, because the orders of the elements have to divide the group order, which means that the orders of those points are either 2 or 4. So we only have to compute twice the point or 4 times the point. What trick they do in the book is that they remark, but I think that's not so easy to see. I don't understand what they want. I think they just leave something out. Because in the book they write that we see that 3Q is minus Q, but I think that's not easy to see. We actually have to use our formulas to compute that. So the duplication formula, let me just check if that's really correct there. Because this is the duplication formula from chapter 2, section 1, where they don't have the short Weierstrass form yet, and I changed that. But I think
I made a slightly different calculation. I just calculated the tangents, and they are the diagonals through the 0 point. So 2p will be 2q will be p, and so is 2 times r. So the tangent has slope 1 in the case of q, and I think in the case of r, the tangent has slope -1.
yeah, so basically what you did is what they did in the book when they derived the explicit formulas, and you put it in, and then you saw that that 2q is p, right? Okay. Let me just say, which is basically also the same as using the explicit formulae. Okay, So if we now know that 2q is p and p is a torsion point, we also know that q is a torsion point, and we already know the order. Because p is not the point at infinity, then q has order 4. And the same goes for r, because r is just minus q. So 2 times r will be minus p, which is p. So r is also order 4. And with this information, we can also see which group this is. Because z mod 2z squared has only points of order 2, but we have points of order 4. So our group, I hate these boards. This cannot be, yeah. So this has to be z mod 4z, because this has is already the point at infinity. This has order 2. So if we identify that with 0, 1, 2, 3, 4, then this would be 1 or 3, and this would be the 2. So this is z mod 4z. And is this a possibility in Mazur's theorem? I erased it, but yes, of course it is. Yeah. Okay. I would stop here. It's 5 minutes early. I think we should actually be here until 50, but yeah, I thought I would need more time for this. So thank you very much for your attention. See you next week.